Hello? Oh, brilliant, thanks. Right, well, that's the worst bit over. So thank you very much for those of you who are still with us. It's the final session, so to speak, and for me, actually, personally, the one that's most interesting. We want to move away, in some sense, from science and towards economics and engineering. And the real question is, what's the future for storage of renewables? So we've got two talks back to back. So Don gets the second tranche. He gets a second chance to talk to you, and he's going to shift from speaking about the history to what he sees as the future. And then immediately after that, we'll have Ian. Where's Ian? Right. Ian's come up from Imperial, and he's an expert. I think you have a mixed background in physics and economics, is that? So quite, and a couple of other things, so quite unusual. But an expert in the economics of storage. And so he's got no vested interest in liquid metal batteries, and he'll say what he thinks are the issues and where we have to go from here. So that'll come back to back, half an hour each, or maybe a bit less because I've taken too long. Originally, we were then going to break for coffee and then come back in for a discussion session. But I actually think, and I spoke to Tom, we agree, Maha's kindly agreed to go along with us. What's best is if straight after the second talk, we go immediately into the discussion. So what I would suggest is that after Don's talk, if you have any quick questions for clarity, ask them then. But if you have any major questions, maybe hold back until after the second talk. The same for Ian. And then hopefully we'll get a nice discussion going at the end of both talks. Is that fair rules of engagement?
Everything's fine.
Okay. So please welcome Don for his second talk.
Okay. So this is the surprise talk. I was invited to talk about the history of the liquid metal battery and to give you some insights into how I arrived at what we have. But then I was approached to talk about this, the challenges of commercialization. So let's take a look. I'm going to do this rather quickly. The point of departure was the specifications. That's exactly how I started the whole enterprise. I didn't invent a battery and then say, what's the potential application? So these specifications had to be there. I showed some of this yesterday. Long service lifetime, safe, fire resistant, operationally flexible, long duration, and also rapid remediation of changes in supply and demand, and a super low price point. And it had to be all of them. So what are the challenges of commercialization? So first thing was to secure the IP at MIT, because already my students were coming to me. David Bradwell said he was hoping that this would lead to a spin out and a startup company. So we were already mindful of how we were conducting the experiments in such a way as to file disclosures of invention that would ultimately lead to filing of a patent application. The work was done at MIT, and so therefore MIT is going to own the IP. That's the way the rules are. And so we got the application out, and by around 2010, David Bradwell and Louis Ortiz came to me and said, we know enough, let's start the company. And as I told you, I was squeamish about the company. I thought it was corrupting and so on, but they said, if you want to change the world and have science and service to society, you have to follow the technology, otherwise it will perish. So we got together with some attorneys and incorporated the company. And then, because MIT owns the IP, we had to secure the license from MIT. This really, I don't know if you know this expression, it jars my pickles, that I conceived the idea, I raised the funding, I put together the team, we do the research, we secure the IP, and then when I start the company, I have to license the invention that I invented back from MIT. But that's the way it is. If you wonder why, innovation isn't rampant, then they say, we're innovation hubs, we accelerate. No, you don't accelerate. You impede. You impede. So we licensed the IP from MIT, and then we had to do the fundraising, Series A investment, and this was 2010. By then, the bloom was off the rose for storage, because there had been all these failed companies in the mid-2000s. And then, of course, there was that scandalous one that came out of MIT, the A123 thing, which those guys should all be wearing orange as far as I'm concerned. But it cast a long shadow. We managed to secure the Series A investment. There was Bill Gates and Total. And then now the clock is ticking. It was a modest amount. It was $4 million. And the clock is ticking, because now you have to take this thing from where it was, which was in a coffee cup size at MIT, and you have to be able to demonstrate that it's scalable, because you're going to need more money than $4 million to get to manufacturing. So you can't go out and raise a Series B saying, we're full of aspirations. No, people are going to say, where's the progress? Where's the delta? So that meant we had to get space and personnel. And personnel means both technological people. Some of them were former students. They wanted to come and work with us. We had to try to find some other people. We've been talking here for several days about liquid metals and molten salts. You know how big that community is? It's really, really small. And so I basically said, the people that we need to hire will be the people that we have mentored once we've hired whom we hire. We're going to generate the people that we wish we could have had on day one. And we need management people as well, because I don't want to get mired in business decisions. Although I know enough that if we don't succeed as a business, we don't succeed with the technology. But you have to have both. You have to have a technology that scales, and you have to have a business model that ultimately can earn revenue, because that's what the clock is ticking for. I can raise more money, but when I raise the money, I have to sell equity. And pretty soon, I own next to nothing in the company. The inventor is diluted to almost zero. That's the blunt truth. I mean, you might read of the odd person. He started a company, did some software, and in 3 months' time, he's a billionaire. That's not here. This is tough tech. And so the sooner we can get a revenue stream, that means then we can get all the money we need by going to the bank. Just as if you try to get a mortgage, you can't get a mortgage unless you have an income. No bank is going to give you a mortgage if you don't have an income. Well, once we have an income, we don't have to sell equity. And we need a work plan, because people are going to ask, well, what's your point of departure? And it's not electrochemistry. It was all about learning how to build this thing at scale. And we had conversations yesterday about, what should be the practical cell size. The battery, as you know, battery, if I hit you once, it's assault. If I hit you more than once, it's battery. Battery means plurality. That's why they call the person that's up at bat, they call that person the batter, because that person is going to swing many times. So the battery has a plurality of cells, and which you don't, initially, Vietz correctly reminded me about how there's some video footage out there of me talking about this one big battery the size of this room. Well, I thought it was cool because I'd seen an aluminum smelter, but we quickly came to realize that to manufacture these things and put them inside a 40-foot shipping container, we need to have something that's big enough that we're not playing with little 18650s or AA's, but not so big that the 16-inch cell that we had, the 1 kilowatt hour, it weighed about 150 kilograms, and we couldn't even move the thing around the lab. And big problems. How many of you have talked about the anode-cathode distance, the distance between the negative and the positive electrode, and how that thin electrolyte determines the joule heating? But what happens if you've got 3 current collectors coming in from the top and they're just a little bit off of true? So that means if the interelectrode gap is shorter over here than over here, the preponderance of the current is going to not short, but it's going to flow over here. And then the whole thing is just a mess. So we had to demonstrate that we could upscale, and that meant going to the first stage and the second stage and third stage. And we very quickly came up against supply chain issues. We had to be able to source all of the components that we need. And we couldn't just call up liquidmetalbatterysupplier.com. There is no such person. So we had to develop all that. And then quality control. You know, not only, we had to do the quality control on the inputs. We were shafted on a number of occasions because we had certain parts that were being fabricated, and the initial parts that we received were good. And then over time, unbeknownst to us, somebody at the supplier changed one of the performance parameters, changed the annealing temperature, some such thing, and the parts were failing. So at that point, we said either we build everything ourselves, which means it's going to delay us, or we have to have quality control on everything that comes in the door. And then after we've made it, we have to test each of these cells. At the time, they were about 10 centimeters square. So 4-inch square and about 4 centimeters tall. Each one of them was about, I don't know, 40 to 60 amp hours. And then end of line, develop all that testing. Ultimately, we would like to get to the point where we could be testing them statistically. But initially, everyone has to be tested. And by tested, no, there's a voltage. No, they have to be stress tested. They have to be stress tested. And then eventually, we're going to get enough of these that we can aggregate a plurality of cells and make a battery. And the very first battery that we built has to be a battery that is self-heating. So that means, what's the critical size? There's a modeling question. How many of these do you have to put together? And we reasoned it was going to be about 15 kilowatt hours. And we put enough of these cells together in aggregation, and then what kind of insulation do we put, and so on and so forth. Battery management system. We couldn't use anything from lithium ion. We developed that. We had our own circuit boards designed and manufactured for this, and on and on and on. And we built this thing, 15 kilowatt hours, heated it up, and it worked. It worked. We actually got power coming out in obviously less than what we put in, because there's a round trip cost of charging and discharging. As people rightly pointed out, when you discharge, you get less than the open circuit voltage, and when you charge, you have to pay more than the open circuit voltage. It's easier rolling downhill than it is running uphill. Gee, that's deep, isn't it? What else? The seals. That was a killer. That nearly killed the company. For 2.5 years, I remember one day when our CEO came in and to an all-team meeting. We probably had about 35 people. He said, "Ladies and gentlemen, this is no longer a battery company. It's a seals company. If we don't have a seal, we are out of business." And it had to be, and you've seen some other presentations today, showing the feed coming through the top, connected to a mesh, and that member has to be an electronic conductor. It's a metal, but the can is a metal. And so it has to be dielectric collar on that that's hermetically sealed, and it has to be able to endure the expansion that accompanies going from room temperature up to, say, 500 degrees Celsius. And what happens if there's a failure? We had a whole bunch of cells on test, and they were repairing the Red Line, the subway in Cambridge, the other Cambridge. And there was a big power outage. We were in Cambridge at the time, and all of our cells, right from, I was in a MIT medical, in a doctor's office for just some checkup. It was about 4:30 in the afternoon. This is right this time of year. Everything goes dark from Charles River, Cambridge, at MIT, all the way up to Harvard Square. All of Cambridge went dark because one of the workers made a mistake on how to shunt the power line for the subway around this one station at Central Square where they were doing some repairs. And everything went dark for many hours. So all of our cells plunged. They all cooled. The next day we came in, the power was restored, and they all came back on again. So we demonstrated, we weren't planning this test, but we were shock tested. And it showed that the collar that we had designed was stable. Well, we had to go beyond that, and there were other episodes where the collar would fail after, say, about 6 months of operation. So that was a big one. And, you know, it would have to be a ceramic, and it could be something, you know, I could put things like yttria, zirconia, all of these fantastic things that have metal ceramic bonding and so on, but it has to be to a cheap price point. You can't have a $5 cell with a $100 collar. So that was a big problem. That really killed. So that was one. And then, as I showed you yesterday, as the price of lithium-ion batteries dropped, then people looked at us and said, well, you're gunning for $270 a kilowatt hour. Lithium-ion is going to overtake you. And I said, but lithium-ion is stupid. You don't make a 100 megawatt hour facility. But these people, they don't understand this stuff. They said, this is cheaper. Why would they buy this unknown technology? So we had to pivot. So we went from lithium lead antimony to lithium bismuth, and then ultimately to calcium antimony. And along the way, certain investors dropped out. So that was really hard. And we didn't do a lot of marketing in the early days because I felt we're a tech company, we don't have our technology yet, so what are we going to be marketing? Because the first question people are going to ask, how much does it cost and when is it available? And I can't answer either of those questions. But ultimately, you know, with all of the people who are fraudulently working in this sector, we had to start talking about the attributes of lithium-ion battery and being able to set ourselves apart, because there were competitors, which is fine, I expect that. It's a big market, there's going to be many battery chemistries. But there are also detractors. I mean, some people are just really vicious. Yeah, I told you yesterday, I was never greeted with bouquets of flowers. But there was all kinds of nasty stuff. And, you know, with social media and World Wide Web, people can write all kinds of nasty stuff. But I don't engage, and I made sure that we were never engaging either. We never disparaged our competitors. I said, just make a product that works. The market is a cruel arbiter. If you have a better product, the market will figure it out. It doesn't matter what these other people say. But it did affect us when we were trying to raise funding. So there were lithium-ion, as I said, and then there were these others. There's flow batteries and metal air batteries, and there was Zebra. You know, GE had the Durathon, and we just had to be able to say, well, we can succeed, but prove it. It doesn't matter what I say. You know, show me the thing working at scale. And yeah, so we had to endure investor fatigue. Many of them dropped out. Fortunately, Bill Gates stayed with us the whole way. Some new people joined. So there's that. So as I told you last day, Ambread's 12 years old. It's hard to believe. It's 12 years old. Microsoft has announced that they will buy our batteries for firming up their solar-powered big data farms, cloud computing things. There are many people that are interested in ordering this now. And the last time I looked, there was the order books with some hundreds of millions of dollars. And then we don't have the manufacturing capacity. We weren't going to build a factory without orders, and we weren't going to get orders until people had confidence. So this is the chicken and egg situation that you're in, conundrum. So now we're moving to Milford, Massachusetts, and this is real. This is no longer just aspirational. And so this year in June, I was given the European Patent Office Award for the liquid metal battery. I was totally surprised by this. And because we had patented not only in the United States but elsewhere, including in Europe. And they have a ceremony every year. It's probably going back about 16 years. And there is one category for people from non-European Union countries. And so this was nominated for non-EPO member category, and it's conducted like the Academy Awards. You do not know. And so you do know if you're a finalist. So there was myself and 2 other technologies that were finalists. So I was there, one of the other people was there, and then the third party, they were on a Zoom call or something. So we're all sitting there, and there's a whole bunch of other awards. There's awards for under 30, young inventors, and then there was a Lifetime Achievement Award, and there was some other award like for European patents and so on. And so we're sitting there, and there's this woman here on the right, and she's, I don't know, somebody might know her, but I think she's from Portugal, but she does some show in Europe. So she was the master of ceremonies, and she's conducting all of this, and we're sitting there, you know, and like, you know, here's the best film from, you know, and so we're just sitting there. I'm sitting there thinking, you know, I'm just wasting my time here, but okay, I came to Munich, whatever. And then they come to announce this best award, and this was she's got the envelope there and had just opened it up and said, it's Donald Sadoway. I said, I'm hearing things. So I got up there, and they had the award, which is this sculpture here. It's digitally printed. It's made out of sand, but it's digitally printed. Okay, fine, I'll take it. Anyway, so that was, and that generated a lot of publicity in the United States, because the U.S. Patent Office doesn't do anything like this, because that wouldn't be fair. Like, because in U.S., everybody's awesome, right? So every child that touches the soccer field gets a trophy, you know. Well, here they actually chose somebody, so that was nice. Okay, and then in September, the Wall Street Journal ran a story on stationary storage. They did a feature on Ambry, and this is Ambry in Marlborough, Massachusetts, behind me. This is a gigantic wall of cells that are under test and so on. They also featured this startup with the metal air battery, Form Energy, which I think is a complete fraud. And so they had the photograph of this, and they had a photograph in front of me is a table with all of these cells, and somebody earlier today showed me holding this thing. It has a capacity of about 100 amp hours in a single cell. All these cells sitting there. For the Form Energy, they had a cartoon that looked like it came out of a child's science book. They have nothing. They have nothing. When you see a company with no imagery, all secret what they're doing, no data, no publications, no patents, something's wrong. You know something's wrong, but the business writers are just right. Anyway, so that was it. So I think this is probably a good place to stop. We'll keep us on time, and I'll turn it over. Yeah.
Thank you very much. So I suggest we take a few short questions now. Don't forget, you get a chance to come back after Ian's talk. So anyone? Yes. Oh, we'll take you first.
Correct. Yeah, after a lot of trials, tribulations. So it was a combination of new material sets and also a redesign, so that the way the system changes shape over thermal excursions, it doesn't put, it's obviously there's ceramic in there. And some of your materials. There's some nitride in there, and there's ceramic metal, bonding, brazing, everything. And then to make sure, if there's a ceramic, make sure that the ceramic never goes in tension. The ceramic can survive stress under compression, but it cannot survive stress under tension.
Rich, I think you had a question.
So I've watched many episodes of Dragon's Den in the UK. I don't know if you're familiar with that program. I think it's called Shark's Den in the US or something. Anyway.
Yeah, I'm sorry, I haven't watched that.
Okay, so I was going to ask you, do you have one product, one battery for mass production? And do you have a minimum sale? So do you only sell a minimum number of batteries?
Okay, do we have a battery? Yeah.
Just one. Is it one, or is it one product?
No. we're manufacturing cells, and then the customer will say, let's say the customer wants 100 megawatt hours of storage, then we can work with the customer to figure out what is so there's the optimum cell size, and then there's the optimum battery size. As I told you, you can probably in a 40-foot shipping container get the equivalent of about 1 megawatt hour. So somebody wants 100 megawatt hours, you might have to have 100 of those containers. If somebody, or maybe we can start exploring, do we want to make something larger? But we were already thinking about shipping down the highway. You realize today the technology is so good for making the wind turbines that the nacelle, one of the blades, it can be made so long that you can't send it down the roadway because it can't make the turns. So those big ones, either that or they figure out a way to assemble them on site, and I can't imagine doing that. But anyway, so we were thinking about having the unit battery size, not the unit cell size, but the unit battery size to be some multiple of the size of the 40-foot shipping container. That way you'd be able to put that on a truck and send it down. So the answer to your question is, obviously we can't get much below, I don't know, 20, 30 kilowatt hours. If we get down, like we made the 15 kilowatt hour, but boy, it needs more to have the thermal mass that will allow it to undergo charge, idle, discharge, idle. But getting big, no problem. Just keep adding cells.
Any more questions?
For the insulation, I know from sodium sulfur batteries, they use some kind of vacuum insulation where they put thin metal sheets around that the heat is reflected. Do you use something different or the same?
I don't know all the details about sodium sulfur batteries, except that I know that because they have the beta aluminum membrane, that was their undoing. But we, in the individual cells, we're charging them obviously with metal and salt, and then there's a gentle reverse pressure, and then backfill with some inert gas, argon, and then we weld the top shut. And after that, we don't touch them.
And the whole stack, that the heat stays inside?
So those things are put on trays, and then the trays go into brackets inside the shipping container. And then, of course, they all have to be connected. They have to, because the battery, you don't want 1 volt. You need, like, to get to the size that will make them useful for the grid, they have to get up to, say, about 400 volts or so. So we connect them. And that was another thing. You can't use copper wire. Copper cable at 500 degrees C will oxidize. It's useless. And we were using nickel. And nickel works, but it's terribly expensive. And so I came back to them and I said, I'd worked on the inert anode for the aluminum electrolysis cell. I said, make an aluminum bronze. Take copper, add 10% aluminum. Guess what happens? It oxidizes and forms aluminum oxide on the surface of copper. Not the combined aluminum copper oxide. Aluminum oxide, shrink-wrapped copper, and it works. So all of that is done and then goes into the tray. And then for the insulation at the final, we came with almost like a sand. We just pour it in, let it fall wherever it needs to go. Yeah.
Thank you.
Yeah.
Maybe one last question here, and then we'll move on.
Hey, Donald, just a question about, I guess, monitoring and instrumentation. Presumably, your plan with selling these things is that you're going to kind of keep watch on them, at least in the early stages, before you've sold thousands and thousands of units. Is that something you're kind of, what are you envisaging? That eventually you'll just hand it over to the customer and then they deal with it? Or will it come with a kind of contract where the customer's also effectively bought someone from Ambry that monitors it and sort of...
So let's first talk about monitoring. So we had to invent the battery management system and the power electronics. So that means both the rectifiers and the inverters. So DC, AC to DC, we had to have to charge, and then DC to AC to go back onto the grid. We invented all of that. And then embedded in all of that is the monitoring of the health of what's going on inside the shipping container. Doesn't mean we have to monitor each cell, but you know, some of you know enough electrical engineering to know that I can be monitoring a string, and you know, with FFT and a whole bunch of other things, I can detect if somebody is misbehaving in the string. So it's basically to know what the health is, and then if one of them fails, can you shunt around and so on, so you don't have to take the whole cell down. So all of that is, it's part of the package. The customer doesn't want to buy a kit. The customer wants a big box, says 100 megawatt hours, and has two terminals. One says plus and one says minus. That's all the customer wants. The customer is not going to say, well, you know, I really want to be in control here. They say, no, 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 we want this thing to work.
Yeah, you're selling a service.
That's right, right.
Shall we thank John? Okay, thanks very much.
Yeah, I'm going to take off my thing here.
There's this, there's this.